My name is Frank, and this talk is about optimal planning with global numerical state constraints, as he already said. Okay, so first I'll briefly describe the class of problems that we're interested in. So this can be thought of as classical planning problems with an additional requirement that some state constraints have to be satisfied at all times. These constraints can take various forms. They can be systems of equations, they might be something like PDDL axioms, or they might be something completely different, such as qualitative spatial algebras. Now, the important feature here is these constraints are difficult to handle in the existing planning paradigms, but there might exist effective solvers that are good in dealing with them. However, these solvers might not always be the best way to model and solve the planning portion of the problem. So what we're interested in is combining the classical planning techniques with these solvers, and that's what we did, and that's what this talk will be about. So here's an example problem, that is power network reconfiguration. Here's an example power network. It has a number of generators, a number of loads. It has power lines connecting the network elements, and it has switches that can be either open or closed. Now the goal is to reconfigure a network, and there are two things that we control. First, we have our discrete action, which involves opening and closing of the switches. Secondly, we can vary the generator output, which is a continuous variables. However, we are subject to a number of constraints. First, we need to make sure that we don't violate any of the laws of physics, otherwise our plans will not be executable in reality. Secondly, generators and power lines have limited capacities and we are not allowed to overload them. Also, if there are any faulty buses on the network, we are not allowed to supply them with power. Now, the flow of power in the network can be modeled in various ways, in various levels of detail. The most accurate is the AC model. However, it's also most computationally expensive ones. There are various simplifications and relaxations, and the one that I will be referring to throughout this talk is the linearized DC power flow model. The important feature here is the flow of power in each of the lines is dependent on the state of the whole network. A single discrete action, that is opening or closing of a switch somewhere, can affect a flow of power in a line that's dependent on the state of all the other switches. That is, before applying an action, we need to make sure that none of the constraints are violated. Now I'll talk a bit about the planning formalism, and I will be using our power network reconfiguration as an example. So we make a distinction between primary and secondary variables. Primary variables are over finite domains, and they function exactly the same way as in classical planning. That is, we have states which are defined as full valuations over the primary variables, and since actions are transitions from one state to another, action effects are defined as, assigning new values to some subset of primary variables. In our power network domain, primary variables are states on the switches. We also have secondary variables, and these can be real numbers. They don't have to have discrete domains. And in our power network problems, this involved power flows, phase angles, generations in the generators, and consumptions in the loads. Now, the way the primary and secondary variables interact is through switch constraints. They're of this form. Phi implies gamma, where phi is a formula only over the primary variables. We call this a trigger. Gamma is a formula only over the secondary variables. I'll illustrate this with an example. So here we have two buses connected by a power line, and there's a switch like controlling the power line. This is the trigger saying that the switch is open. This is the right-hand side saying that the flow of power has to be 0. So this switch constraint says when a switch is open, power in the corresponding line is 0. We have some constraints associated with the closed switch. That is, when a switch is closed, the flow of power has to be proportional to the difference in phase angles. Also, either both sides have to be supplied with power, or both sides must not be supplied with power. The switch constraints are used in 3 ways. First, we have invariant constraints which must be satisfied in all of the states. Secondly, we have goal constraints, and the union of invariant constraints and the goal constraints has to be satisfiable in every goal state. Finally, we have secondary preconditions, and for an action to be applicable, a union of secondary preconditions and invariant constraints has to be satisfied in a certain state. Now, what does it mean for a switch constraint to be satisfied? So we have a constraint of this form, phi implies gamma, and if the trigger is true in a given state, we say that the constraint is active, otherwise it's inactive. So given a state and a set of constraints, we can get an active subset. We then take the right-hand side from this active subset and pass it to the constraint solver that tells us whether the resulting set is satisfiable or not. Now, we say that a state is valid if the set of active invariant constraints is satisfiable. Otherwise, a state is invalid. I'll illustrate this with a simple example. So here's a simple small power network. It has a generator and 3 loads. We have these 2 switches. One of them is open, one of them is closed. The fact that this switch is open makes this constraint active and some other are inactive. Similarly for the other variable. So these are primary variables. Now, if we were to take this right-hand side from these constraints, from the active constraints and put it in a solver, we would see that this is satisfiable, therefore this is a valid state. Now we want to apply an action, that is we want to close this switch over there. Primary precondition is that the switch has to be open, which it is. And the secondary precondition is that the difference in phase angles has to be below some threshold value, which it also is. Now we look at the resulting state with both switches closed. We have a different set of active constraints and some of the previously active constraints are now inactive. Now if we were to put this into a constraint solver, we would see that this is not satisfiable and therefore the resulting state is invalid. So this is an example of an action that would classically be applicable because preconditions are satisfied, but it's not applicable in this case because the resulting state is not valid. Now we were interested in implementing optimal planning on this sort of problems, and for that reason we are relying on the A-star search. And we needed a heuristic to guide the A-star search. What we did is we extended delete relaxation to incorporate the state constraints, and we used it to compute H+. Now I'll talk a bit about our extension of delete relaxation. For primary variables, it works exactly the same as in classical case. What we still need to figure out is which of the constraints are active and which are inactive in a relaxed state. We use this value accumulating view of delete relaxation, that is, each variable is associated with a set of values. Applying an action can only add new values to this set of possible values. It cannot remove a value from the set. That is, as we apply more and more actions, this set can only grow, it cannot shrink. Now we say that the switch constraint is active in a relaxed state if this trigger cannot be false in the relaxed state. Again, I'll show an example. So again, we have this same power network, except now we have sets of values associated with variables. Now, because this thing cannot possibly be false, this one is active, for example. This time we will also add a goal. That is, we want the load in the middle to be supplied with power. This is not possible in the start state. So we apply an action, that is, we open a switch over there. Now, as you can see, this set of states grow, set of values associated with the variable grows. This lets us, this makes some of the previously active constraints inactive. However, the goal is still not reachable. is still not reached. We add another action, that is we close this switch over here. Again, it gets this switch into a position that is both open and closed at the same time. This makes this constraint over here inactive, and the resulting set of active constraints together with the goal is now satisfiable. Now, this provides us this relaxation enables us to build a relaxed planning graph. And the relaxed planning graph enables us to do relaxed reachability testing. We use relaxed reachability testing together with the landmark algorithm to compute H+. The landmark algorithm does not interact with the problem through anything other than relaxed reachability testing, so we didn't have to modify it in any way. Now, computing H+ is quite expensive, and adding state constraints doesn't make it any better, doesn't make it any cheaper. So we wanted to find a way of getting more information from this expensive heuristic. And we use this idea from non-optimal planning, which is preferred actions. So in a given state, we take the actions comprising the optimal delete relaxed plan, which we got as a side effect of computing H+. And we think of those actions as our preferred actions. And the intuition behind this is that the actual plan might look somewhat similar to the optimal delete relaxed plan. We combine this idea with the partial expansion A star. That is, we initially only generate preferred successors to a state, but keep the parent on the queue. This lets us fully avoid fully. This enables us to avoid fully expanding all of the states. Now this is useful when occasionally we get to reach the goal without fully expanding all of the states. This is useful when the heuristic is expensive but accurate and states have many successors, which is the case in our power network problems. In our experiments, this resulted in 42.8% reduction in number of state evaluations, and since most of the time was spent computing the heuristic, we get comparable reduction we get comparable savings in time. Now I'll talk briefly about related work. So we weren't the first ones to sort of couple this planner with an external solver, so Piacentini et al. Did it to solve the power balancing problem. They combined temporal planner with an AC power solver. However, they keep the network configuration the same, that is, they don't open or close any of the switches. They keep the topology of the network the same. Therefore, they don't need to deal with turning the constraints on and off, that is, changing the set of active constraints. Then there's planning modular theories by Gregory et al. And they also propose a general way of combining classical planning with non-classical types of variables. They, however, have actions that directly modify the state of those variables, which is different from what we do, and they also don't have any dedicated mechanism for dealing with global constraints. Like us, they have a principled way of deriving the relaxation. Okay, so here's a summary and a bit of a future work. So these sort of problems can be thought of as classical planning problems with this addition of state constraints. The example that I was talking about in this talk were systems of equations. However, we can also work with other types of constraints, such as PDDL axioms or qualitative spatial algebras, and that's basically what I will be doing when I get back to Canberra. Okay, so to tackle these types of problems, we've combined classical planning techniques such as heuristic search, delete relaxation heuristics, and so on with an external solver. An interesting thing to do in the future might be to look at some other techniques such as trying different heuristics, or maybe something like SAT planning or partial order planning, or maybe something different. So heuristic that we chose was quite expensive to compute, so we wanted to get as much from it as possible. And we've sort of developed a way of getting more information from the expensive heuristic. That is, we are using preferred actions in optimal search. And an interesting thing to do in the future might be to see how this performs in classical planning problems. Finally, there's this thing that I didn't really have time to talk about, which is we've tried to do some optimal planning with state-dependent action costs. However, the approach that we developed wasn't very efficient, so this is sort of an open challenge. And yeah, well, that's it. I can talk about state-dependent action costs, and like I didn't think I would go through it this quickly.
If I may start, I understand that you have a correspondence between your primary state space and the power set of the secondary state space.
Yep.
That is the power set of the set of equations. Can you analyze this correspondence in terms of some compassibilities, or a lattice of what's possible, in order to simplify the propagation of the constraints, and which state is acceptable and which is not beforehand? If your constraint solver can do some analysis of the set of constraints beforehand, may this simplify your planning process?
Okay, so we were actually doing something similar to close learning. That is, like, sometimes some sort of solvers can return Y is a set of constraints unsatisfiable. So it can tell you which ones are in conflict. And so this way we can sort of avoid, making this mistake again. That is, if you learn of a conflict, we can sort of add it to a list of known conflicts, and so we don't have to call the constraint solver again. But that didn't really work that well. So.
Any other questions? I have one.
Okay.
So, is there any reason that you choose to extend optimal planning instead of non-optimal planning? And if you decide to do non-optimal planning, then what kind of planner do you think would best suitable to extend to handle this type of concern well?
Well, I don't know. We chose to do optimal planning because, say the domain in which we worked on, which is this power network reconfiguration, it basically prefers plans to be as short as possible because
otherwise.
Yeah.
Okay.
Exactly.
Yeah. Actually, I have one more question. So. Can you use derived predicates and domain axiom to represent the secondary constraints already, or is not enough?
You mean like in PDDL axioms?
Right. Yeah.
Yeah. Well, yeah. That's what I will be doing next. So.
Yeah, but there's no numerical values. You don't have. I mean, like, people haven't really looked at, power flows. Okay. So that just gives you the reachability. So, that this just gives you the reachability relation, but not, like something is feedable by something else, but it doesn't give you the capacity It doesn't give you the power flows, numerical power flows, and cannot enable you to say whether some capacity constraint is violated.
So how about PDDL plus? I know there's no planner that console PDDL plus.
So this is like, this is orthogonal. What PDDL plus has is effects, numerical effects. This is like really almost static constraints, right? This is a different problem.
PDDL plus, you can have event that trigger some process that can trigger down.
Yeah. Yeah, but you imagine the thing here is that every time you change one switch, you switch it on or off, everything changes. So I think that would be a pretty inefficient. I think your process would still have to have like some sort of equation, like that. So but it's not just events. It would be like a massive amount of events.
Okay. Let's take the speaker again, and then let's move on.
Thank you.